Hi there, hope you guys are all doing well. I'm going to try the YouTube thing again and we'll see how that works. It's all kind of a big experiment. Before we get started on today's lesson on the Hubble's law, we're going to do just a really quick review on how we measure distances in space. So this is really quick with very little explanation, so if you want to go back into it a little farther, go back into the modules. And the topic is astronomical distances, and you can kind of go through it again there. Okay, change slides. There we go. All right, so one of the ways that we calculate distances in space is using parallax. And if you remember parallax, it's the angle that we see in the sky. So down in the lower picture there, where it shows Earth, there are two blue blobs. On one side of the sun, when we look on the right side and we look up at the observed star, we see a line from the Earth to the star, and it produces an angle compared to 6 months later when the Earth has orbited around the sun. It's now on the other side, looks at the same star, and creates an angle. So we use half of that angle, that's the parallax angle P. And with a little bit of trigonometry, we can calculate distance with the small angle formula. So that's one way we do it, but parallax only works for the very closest stars, because if you think about it, the farther something is away, the smaller that angle will get. Smaller and smaller and smaller until we really can't measure it any longer. So we have to have a method to measure distances beyond just parallax. So we use variable stars, and these should be familiar to you by now. The Cepheid variables, how they brighten and they dim and they brighten and they dim. And with a charted graph of how many days it takes for it to brighten and dim tells us how big that star is, or what the luminosity is of it, and we are able to calculate its distance. So that's the second way. The third way is a type 1a supernova. So we talked about how supernovas, this particular type, is a white dwarf when it gets too much mass and the core exceeds 1.4 solar masses, and so it explodes, kaboom. So that's the other method. John DeSaker is the man who calculated that 1.4 solar masses, so we can use that as a standard candle. We know it's like the 60-watt light bulb. Wherever it is in space, it should give off just 60 watts. Therefore, if it looks dimmer than that, it's farther away. If it looks brighter than that, it's closer. Another way we can calculate is by the redshift, where the spectra actually moves towards the blue or the red, depending on whether it's moving towards us or away from us. So that is another way we can calculate distance. All right, so there was a time, only 100 years ago, when we just didn't know very much about space. We had pretty big telescopes, we were looking at things up there, but we were still trying to figure it all out. Figure out what a galaxy was, figure out what distances were. And there was a lot of discussion, a lot of disagreement about what was going on. So let's look at what was happening in 1920. So that's when these big debates were going on. So the census of the United States showed the population of the country exceeded 1 million people. Wow. Women were given the right to vote. Took till 1920. The League of Nations was established, ending World War I. The American Professional Football League was established, the NFL. So that's a little bit of history, what's going on at the same time as this debate. So the debate was over these. The debate was over what are these spiral things that we're seeing up in space. And we're familiar with Edwin Hubble, how he calculated it in the end. But before even Hubble came along, there was a disagreement. So they're like, are these within our own galaxy? Is that a galaxy all by itself? just what are these spiral-shaped things that we're seeing up there? So there was a debate in Washington, D.C. in 1920. It was between Curtis and Shapley, and the title of it was The Distance Scale of the Universe. So they were going to talk about the nature of spiral nebulae, the size of the Milky Way, our own galaxy, and the position of the Sun in the Milky Way. So Curtis, he said, we're located near the center of the Milky Way. It's 20,000 light years across, and the spiral nebula, those are outside of it. So that was his whole idea, that was his argument. Now, this is Harlow Shapley. He should be a little familiar to you also because he's the one that mapped all those globular clusters that you guys were putting marshmallows on skewers. He was mapping those to try to figure out distances. And by using his data, he said, no, my friend, the Milky Way is 300,000 light years across, and we are 60,000 light years from the center. The spiral nebulae are located inside the Milky Way. So they had an argument, back and forth, back and forth. Each of them was right about some things, but wrong about other things. Shapley made the correct deduction that the Sun was not at the center of the galaxy and that the galaxy was much larger than previously thought. He used variable stars, particularly in globular clusters, for his data. Curtis argued convincingly that the spiral nebula were external galaxies, based on many novae seen in the Andromeda galaxy. He reasoned that only so many novae were observed per galaxy in a particular amount of time, so Andromeda must be separate. Our own galaxy was just one of many island universes. Well, nobody won. They were both right about some things, both wrong about some things. They had the size wrong. They had Curtis was right that the nebulae were actually separate galaxies from ours. So they both went home, not really knowing what was right. Until, here we go, we have Edwin Hubble, who came along and was using this giant telescope, the Mount Wilson one near Pasadena, California, which at the time was the biggest telescope in the world. So he uses these Cepheid variable stars in M31, which is Andromeda, and calculated its distance as 1.5 million light years, which is actually about 2.5 million light years, but that was not bad for the first guess. And he said, for sure, galaxies, these spiral nebulae, are separate from the Milky Way. And he used variable stars as well. So he wasn't satisfied with just calculating the distance to Andromeda. He was very curious about these galaxies. So he would look at distant galaxies with this very big telescope and try to find these variable stars within a galaxy far, far away. And by doing that, he was calculating its distance. How far is this thing? So, from the Cepheid's variable period, you can go for how many days it brightens and dims, go up on the chart, go across and find its luminosity. Compare that to how it appears from Earth, and with that formula, the distance formula, we can figure out how far away that galaxy is. So that was part of the puzzle, but he also needed to know how fast it was moving away from us. So for that, he was using the redshift. So remember spectra, how in a laboratory, like in the middle one right there, the lines are supposed to be in a particular place for a particular element. Seeing that that's hydrogen, we would say that the laboratory in the middle stripe there, that's where those lines should be. But when something is moving away from us, all those lines shift towards the red. When something's coming towards us, they all shift towards the blue. So with that difference, we can calculate velocity. So here's what he used. This is actual data from his paperwork. He used galaxies, which are in that diagram there, different galaxies. And he used calcium lines, the calcium spectrum lines, the H and K lines. And he had a spot where they should be, but then he saw that they shifted. And they shifted farther, and they shifted farther and farther and farther as you go down towards those. So the following pictures all are magnified equally. Virgo is closest and Hydra is farthest from the Earth. Notice that the redshift is greatest for Hydra, and therefore the recessional velocity is also the greatest. So how does he get velocity? He gets the redshift. He calculates, the redshift is the first part of that formula with the wavelength sign, equals the velocity divided by c, which is the speed of light, and he's able to get the velocity of how fast these galaxies are moving. And there's the complicated version if you want to sit and calculate it out. It's really not that hard. And it's kind of cool that we can calculate those distances. So here he gets his graph paper out, and he graphs on the bottom the distance, how far they were away from the Cepheid variables. On the left side, he graphs how fast they're moving from us from using that redshift data, and he makes a chart. And it was kind of all over the place. We have dots above the line and dots below the line, but what is very sure about this chart is the farther something is away from the planet Earth, where we're making these observations, the faster they're moving away. Well, he redid it again. So this was in 1929. He redid the whole study again. And the 1929 data is in the lower left-hand corner of that chart. You can see it was not very impressive because they didn't go that far away. But later, in 1931, they went farther away, and the data fits the line much better now. And you can still see the farther something is away, the faster it's moving away from us. This was something they had never thought of before, that things were in the universe were expanding at a very fast speed. It was a new idea. It was surprising, and they just couldn't believe this was happening. So if we look at this chart to kind of explain how things are moving away from each other, there's no middle. You could be B, you could be C, you could be D or E or A, doesn't matter. Whatever spot you are in the universe, everything is moving away from you in the same amount of time, in the direction, every which way they're moving away. So if you look at the top graph, you've got them all spaced that particular way, and then when time goes on, then they all are moving away at those intervals. So Hubble's law, this law that we're learning he came up with, it only works for distant galaxies. For nearby galaxies, like in our local group of galaxies, stars inside the Milky Way, and for objects in our solar system, the relationship between distance and velocity does not hold. The reason for this discrepancy for nearby galaxies is the peculiar velocity of the galaxy, that is, its real velocity through space that's unrelated to expansion. I'm going to stop there because I've got to keep talking and my time's up on this one.